The decision to connect a generator as a separately derived system, or SDS, versus a non-SDS configuration hinges on several key factors. These include load types, voltage configuration, system grounding, electrical code requirements, and generator size. Load types significantly influence the choice. SDS connections are generally preferred for loads that demand a solid neutral reference. These include sensitive electronics, uninterruptible power supplies often called UPS, and medical equipment. On the other hand, non-SDS connections are typically suitable for loads that do not require a solid neutral. Examples include motors, pumps, and general lighting. Considering the generator's voltage configuration is crucial. Delta generators lack a neutral connection inherently, making them unsuitable for SDS configurations. Y generators, however, do have a neutral connection and can be configured as either SDS or non-SDS. System grounding also plays a vital role. Solidly grounded systems require a neutral that is consistently connected to ground. SDS connections are usually favored in these scenarios. Conversely, ungrounded systems do not have a neutral connected to ground, making non-SDS connections the preferred choice. Electrical code requirements, such as those outlined in the National Electrical Code, often dictate the connection type. The National Electrical Code, or NIC, mandates SDS connections for certain standby power systems, notably those serving healthcare facilities. Non-SDS connections may be permissible in other applications, but consulting local electrical codes for specific regulations is essential. Generator size can also influence the decision. Larger generators often provide improved voltage stability and fault protection when connected as SDS, particularly when serving critical loads. SDS connections offer several advantages. Firstly, they provide a solid neutral reference for sensitive loads, ensuring stable and reliable operation. Secondly, they contribute to maintaining voltage stability during generator operation, preventing fluctuations that could damage equipment. Thirdly, SDS connections ensure proper grounding of equipment, enhancing safety and reducing the risk of electrical hazards. Non-SDS connections also offer advantages. Firstly, they often simplify generator installation and maintenance, reducing complexity and labor. Secondly, they may result in cost savings compared to SDS connections, as fewer components and less labor may be required. Thirdly, non-SDS connections are well suited for specific types of loads that do not require a solid neutral, offering a practical and efficient solution. Ultimately, the installer's experience and preference can also play a role in the decision-making process. Some installers may favor SDS connections for all generator installations, while others may recommend non-SDS connections for certain applications based on their specific characteristics and requirements. In conclusion, determining whether to install a generator as SDS or non-SDS requires careful consideration of various factors. This involves assessing the specific requirements of the loads being served, the generator's voltage configuration, system grounding practices, adherence to electrical code requirements, and the installer's expertise. By thoroughly evaluating these factors, one can make an informed decision that ensures optimal performance, safety, and reliability of the generator system. To reiterate, the decision between SDS and non-SDS generator connections depends on the interplay of load characteristics, generator type, grounding practices, code compliance, and installer expertise. For loads requiring a stable neutral, SDS is preferable. Delta generators necessitate non-SDS configurations. Solidly grounded systems benefit from SDS connections, while ungrounded systems favor non-SDS. The National Electrical Code mandates SDS for certain critical applications. Larger generators often perform better as SDS. SDS connections offer a stable neutral reference, voltage stability, and proper grounding. Non-SDS connections simplify installation, reduce costs, and suit loads not needing a solid neutral. Installer's experience also guides the decision. In essence, a holistic evaluation of these factors ensures an appropriate generator installation. Let's delve a bit deeper into each of these aspects, starting with the load types. When dealing with sensitive electronic equipment, a stable and reliable power supply is paramount. Fluctuations in voltage or current can cause malfunctions, data loss, or even permanent damage. Devices like computers, servers, and network equipment rely on a clean and consistent power source to operate correctly. SDS connections provide a dedicated neutral reference point, minimizing the risk of noise and interference that can disrupt these sensitive loads. Uninterruptible power supplies are designed to provide backup power in the event of a utility outage. They typically include batteries and power conditioning circuitry to ensure a seamless transition to backup power. UPS systems often rely on a stable neutral reference to function correctly, making SDS connections the preferred choice. Medical equipment such as patient monitoring systems, diagnostic equipment, and life support devices demands the highest level of power reliability and safety. Any disruption in power can have serious consequences for patients. SDS connections help to ensure a stable and grounded power supply, minimizing the risk of electrical hazards and equipment malfunctions. On the other hand, loads like motors, pumps, and lighting are generally less sensitive to power fluctuations and do not require a dedicated neutral reference. These types of loads can typically operate effectively with non-SDS connections. Now, let's consider the generator's voltage configuration. Delta generators do not have a neutral connection, making them inherently unsuitable for SDS configurations. In a delta system, the three phases are connected in a closed loop with no connection to ground. This configuration can be advantageous in certain industrial applications, but it does not provide a neutral reference point. Y generators, in contrast, have a neutral connection that can be connected to ground. In a Y system, the three phases are connected to a common neutral point, which is typically grounded. This configuration provides a stable neutral reference and allows for both line-to-line and line-to-neutral voltage connections. As a result, Y generators can be configured as either SDS or non-SDS, depending on the specific application requirements. Moving on to system grounding, solidly grounded systems require a neutral that is consistently connected to ground. This type of grounding provides a low impedance path for fault currents, helping to quickly clear faults and minimize the risk of electrical hazards. SDS connections are typically favored in solidly grounded systems because they provide a dedicated neutral reference point that is directly connected to ground. Ungrounded systems, on the other hand, do not have a neutral connected to ground. Instead, they rely on other grounding methods such as impedance grounding or corner grounding. Ungrounded systems can be advantageous in certain applications where it is desirable to minimize ground fault currents. However, they also require more sophisticated fault detection and protection schemes. Non-SDS connections are typically preferred for ungrounded systems because they avoid the creation of a direct ground path through the generator neutral. Electrical codes, such as the National Electrical Code, play a significant role in determining the appropriate generator connection type. The National Electrical Code mandates SDS connections for certain standby power systems, notably those serving healthcare facilities. This requirement is intended to ensure the highest level of power reliability and safety for critical medical equipment and patient care areas. For other applications, non-SDS connections may be permissible, but it is essential to consult local electrical codes for specific regulations. Local codes may vary depending on the jurisdiction and the type of facility being served. Generator size can also influence the decision. Larger generators often provide improved voltage stability and fault protection when connected as SDS, particularly when serving critical loads. This is because larger generators typically have lower impedance and can better handle the sudden load changes that can occur during generator operation. SDS connections help to ensure that the generator's neutral is properly grounded, minimizing the risk of voltage fluctuations and ground faults. SDS connections offer several advantages, including a stable neutral reference, voltage stability, and proper grounding. A stable neutral reference is essential for sensitive electronic equipment, as it minimizes the risk of noise and interference that can disrupt operation. Voltage stability is important for all types of loads, as it helps to prevent equipment malfunctions and damage. Proper grounding is crucial for safety, as it provides a low impedance path for fault currents, helping to quickly clear faults and minimize the risk of electrical hazards. Non-SDS connections also offer advantages, including simplified installation, reduced costs, and suitability for certain types of loads. Simplified installation can save time and labor, while reduced costs can make generator systems more affordable. Non-SDS connections are well suited for loads that do not require a dedicated neutral reference, such as motors, pumps, and lighting. Finally, the installer's experience and preference can also play a role in the decision-making process. Some installers may favor SDS connections for all generator installations, while others may recommend non-SDS connections for certain applications based on their specific characteristics and requirements. It is important to choose an installer who is knowledgeable and experienced in both SDS and non-SDS generator connections. In summary, the decision of whether to install a generator as SDS or non-SDS depends on a variety of factors, including load types, voltage configuration, system grounding, electrical code requirements, generator size, and installer preference. By carefully considering these factors, one can make an informed decision that ensures optimal performance, safety, and reliability of the generator system. Remember to prioritize the specific needs of the loads being served and to consult with qualified professionals to ensure compliance with all applicable codes and regulations. The choice between SDS and non-SDS is not always straightforward and requires a thorough understanding of the electrical system and the equipment being powered.